Welcome. Today we're going to learn about integration with trigonometric substitution, and this video is actually my third video on this particular topic. So in the example in this video, if you look at item 1, we're trying to integrate a fairly complicated integral. And one of the keys, or clues I should say, as to how we should proceed is that the denominator is you have a square root of something in the form of u squared minus a squared underneath the radical, where u represents a variable. So in our case, the u is x, and we actually have u squared being x squared. And the a in this case represents 4, 4 squared being r16. So again, when you have something in that form, a good choice is to use trigonometric substitution. And one of the reasons we do that is because this form is similar to that of the Pythagorean theorem, and we're going to actually use a right triangle and the Pythagorean theorem to make some trigonometric substitution, and then we're going to integrate that, and then we're going to substitute back. That's the idea here. Now, there are other forms in which this works, and the forms are item 4, that form, and the form I've shown in item 5. These are other forms, and I have videos to show what you do in those cases. Okay, so as I said, we have this form, square root of u squared minus a squared in the denominator. So what we're going to do is we recognize this has to do with the Pythagorean theorem. So we create a right triangle. You can see that in item 3 with theta. And what we're going to do is we're going to manipulate what we have under our radical around this triangle so that it all makes sense using the Pythagorean theorem. And in this form, you want to use the radical as the opposite side to theta. So that's where we've placed it. And then we place the u in this case, which is x, as the hypotenuse, and the a in this case, which is 4, as the adjacent side. If you do that, then things work very nicely for you. In item 4, from our triangle, we identify that x over 4 is actually the secant of theta. And we begin there. That's where you want to begin when you have this particular form. And we know that it's the secant of theta using SOHCAHTOA rules. If you're not familiar with SOHCAHTOA, I do have videos that demonstrate that. Okay, so as we said, we begin in item 3 with x over 4 being secant of theta. Now, what we want to do in item 4 is we solve for x by bringing the 4 to the right side of the equal sign. When we solve for x, that allows us to solve for dx, because when we make our substitution into our integral, we have to always replace the dx. So, what we're going to do is take the derivative of both sides of the equation in item 4, and that yields what we have in item 5. dx equals 4 secant of theta tangent of theta d theta, because that's the derivative of secant. And then we have a replacement now for the dx in our original integral. Another thing that we have to replace in our original integral, and that's noted in item 2. So if you look at item 2 in the center of the screen, we have the original integral. We know what we're going to replace dx with, but what are we going to replace that radical in the denominator with? Well, we go back to our triangle. If you look at the triangle, you have the radical as the opposite side, and we also have a constant on the adjacent side to theta. And you want to use the combination of the radical and the constant. You don't want to combine it with the x because that gets a little bit nasty when you have another variable. So if you take the radical over the constant, in this case 4, well, using SOHCAHTOA rules, that means opposite over adjacent, and that is our tangent of theta. So that's what we have in item 6, that square root of x squared minus 16 over 4 is equal to the tangent of theta. Then in item 7, we just bring the 4 to the right side. The reason we did that was because we don't really want the whole fraction. We just want to solve for square root of x squared minus 16 because that's what's in our integral. And then we replace what we have in our denominator of our integral with 4 tangent of theta. Okay, so if you move over to the right side of the screen, you see in item 8 that we've made all those substitutions. We replace the dx with 4 secant of theta tangent theta d theta, and we replace the denominator with 4 tangent of theta. So what we have now is an entire integral that is in terms of theta and d theta. No longer do we have any x's or any dx's. And then we want to simplify. So in item 2, we make some simplifications, some cancellations, and we have the integral of secant, which is a very basic integral. You can look that up. And in item 3, we have noted that the integral of secant is equal to natural log of secant plus tangent plus a constant. Now this is great. We've done our integral, but the problem here is that everything is in terms of theta, and we want to go back to something in terms of x, because that's what we started out with. So we need to replace or substitute back for our secant of theta, which we have in item 4, and we're going to replace that with x over 4, which we calculated earlier using our triangle. We are going to replace the tangent of theta with square root of x squared minus 16 over 4, which we also calculated earlier. And once we do that, and if you hadn't done that, you could also go back to our triangle, and you can see that that would make sense using SOHCAHTOA rules. Now we just do a little more simplification. In item 8, we noted that the denominator, when we divide by 4, we can use natural log rules, and we can actually make that minus natural log of 4, and that's actually a constant, which means we can combine it with our C1 because they're both constants, and we can just call it C. And that's what we've done in item 11. And we are now have completed our integral. And that is integration with trigonometric substitution. Now go practice, practice, and practice some more.